Good time talking about what it is we're doing, why it works, why it's logical and not just some magical, we just plug some stuff in and out comes this number and we just trust that it all makes sense, okay? So what I've set up for you guys is here, and we'll probably play around with some disk method and washer method here just as kind of an intro to all of this. I've set this up. You can see the higher function is f of x, the green function is f of x equals sine x. The lower function is essentially just the x-axis. And so what I've done here, I'll do a little marking on this before I do any animation stuff. This red region right here is the region that I'm going to be working with. That'll make sense. Bounded on the right by a vertical line, roughly at the high point of the sine curve there. And then below by the x-axis and above by the sine curve. Yes? Okay. So, like I kind of showed you last time, what we're going to do with something like this is we're going to take it and we are going to rotate that red region around the x-axis, creating a solid. And so I'm going to I'll start off with this. So if I revolve this region, it's now gray. We can kind of see this solid forming. There we go. Can you see it? It's like almost 3/4, or about 3/4 of the way done. And then if I complete that, then it'll eventually complete. Okay, so we created this solid region. Like it's completely solid. You can't see through it in any way. And that'll be important when we start talking about disks and washers and that kind of thing. But what we're going to be doing is we're going to be finding the volume of that. Okay? So this is like a higher tech version of what you saw if you did the intro video. Here is what is actually happening. Notice I set n equal to 50, just so you can get a good look at the region, or the solid formed by that region. I'm going to back this off quite a bit. Maybe, okay, I like that. To n equals 9. So that means essentially there are 9. We can count them if we so choose. 1, 2, 3, 4, 5, 6, 7, 8. There's 9 or 10 of them in there. I don't really feel like counting. Oh, I think I counted that little ball at the end. I think I counted one extra. Would you guys agree with me that these, now I'm dating myself here big time, but would you guys agree with me that those things that are in there, those yellowish dark things, they look like DVDs?
Sure.
CDs? Blu-rays? I know, I realize these technologies are like obsolete within like 10 minutes, but whatever. I know it's not YouTube or Apple,
TikTok.
Whatever, exactly. Which will probably be obsolete here in another 3 months, but whatever. Those look like CDs or DVDs, right? Okay. So if you were to look at each one of these CDs or DVDs, we could just extract one of them here, and that's what I'm going to do. I'll take this one and bring it over to here, and I'll three-dimensionalize it just a little bit so we can see it a little bit better.
Nice.
That disk is right there, and then this would be like the x-axis going right straight through the middle of that disk. Does that make sense? Let's break this down a little bit and analyze it. We're going to be trying to find the volume of solids like this. And so, taking you all the way back, I don't know, maybe like 8th grade or something for some of you guys, geometry class, how do you find the volume of a disk like that, aka a cylinder? Really is what that is. Pi r squared times height. That's right. Okay, so we'd say volume for this equals pi r squared times height. But now let's take this and break it down into what we're really dealing with. The radius is right here. Would you guys agree with me then that the radius would be the distance from that axis of rotation out to the function itself, the function's graph itself? Okay.
So it's just the function's graph. Well, no.
What do you mean by, I'm not sure what you mean by,
Never mind.
okay. And then the height would actually be this little itty bitty blue sliver. Can you see it? The height is kind of that thickness. And of course, with a CD or a DVD or whatever, they're really very thin, but there's still thickness there. There is still a height there. Aren't we used to seeing cylinders drawn like this, like the other way? And it's still a cylinder, but it's oriented a different way. Okay, so essentially what we're doing here to find the volume of a solid like this is we're doing sigma of pi r squared h, right? So Peyton, you are one of the most vocal about, I don't get this. So I'd love it if you did get it. Okay. Well, you're just saying, I think you felt like you were just saying from the past, you didn't get this. Okay, so let's add a little bit in here. What if I wanted this to, I wanted to have an indefinite number of these little disks, right? So n of them, right? And so this would allow me then to find volume if there was like 10 or 20 or 30. But you all know where this is going, right? How many disks do I really need to get the true volume? Need to head towards infinity. So I would then say, all right, the limit now as n heads towards infinity, right?
Is that pi r squared n or h?
That's an h. That's the height of the cylinder. So as I put that limit on there as n goes to infinity, wouldn't the height take on a certain characteristic? It would head towards what number? It would head towards 0, so we'd call it a dx. That's right. So I would say,
Why?
so dx is Leibniz's version of an infinitesimally small x. And as the number of these disks goes towards infinity, the thickness of these disks squeezes down towards 0. So, and we call it, we can talk a little bit more about why it's dx specifically. So limit is n heads towards infinity, sigma from I equals 1 to n of pi r squared, and I would now call this r sub I squared, because the r is going to kind of depend on where you are, dx. So what am I really defining here? Say again? Not just the integral, but the definite integral, right? So I would say this is actually the definite integral from some bound to some other bound, wherever I decide to do this, of pi r squared dx. Okay? Why is it dx? This is actually super duper important. I wrote this in the way that I wanted to. This is the x-axis, right? Oops. This is the x-axis right here. Wouldn't you agree here? I'm going to try to squeeze this in here. You see how wouldn't this be the h? I just drew in another blue. Jack, check this out, man. Do you see how this right here, the blue thing I just drew in there, isn't that the h? Do you see how the h is measured as essentially a little tiny difference in the x's? That's why it's dx, not dy or d something else. Okay, and so for those that maybe did watch the intro video and are kind of connecting this, this right here, in this pink rectangle, that is essentially the disk method right there. Okay, so r stands for the distance from the axis of rotation, aka the radius, right? Distance from center to the outer edge. Maybe you see now why the pi is in there, because we're talking about cylinders or little disks. And then maybe you can see why it's an integral, because we need the number of those disks to head towards infinity, squeezing their thickness down towards 0. And as long as we can get the right radius in there and handle our antiderivatives, we're in good shape. We're set up for success.
We can keep the pi on the outside of the integral if we want.
And I would say that's the standard way to do it, what you just said. So I think what you would see in your notes, and I think what I would typically do is start off with this. And so since it's constant multiple, you can just bring it outside the definite integral. And
Is that a problem or something?
so let's do this. I hope that makes sense to you. let's do this. Let's change this up. So instead of oh, come on, you can do it. Come on, computer. We'll refresh this. Okay. So instead of those two functions, let's do these two. Let's go sine of x and f. Let's go 0.2x. There we go. And we'll go from 0 to, oh, what is that, about 2? 2? About 3? Let's see what that looks like. It's a little bit too far. Oh, it's close though. Let's go 2.6. Ooh, that was really close. 5.8. Yeah, I think 2.6 is pretty good. Okay. So I've changed the region here just a little bit. So now my region is going to be, again, I'll color this in for you. My region is going to be right here, this red region. Notice how between, and I'm going to rotate this around the x-axis again, just like we did before. Notice how now there's kind of a space between the region and the x-axis, whereas before the region kind of butted up, like the x-axis was part of the boundary of the region, right? And now the x-axis really is not part of the boundary of the region. It's just this other line hanging out in our picture. So these are situations in which we can rotate around the x-axis or the y-axis or whatever we want. But the shape is going to look decidedly different. So let's see what this looks like if I decide to revolve this. And I'll go all the way out to the 50, and that's 50 rectangles, of course. So if I revolve this, oh, I want a solid. Solid. There we go. If I revolve this, you can see that the shape is pretty different than what we just had. Notice how when I pick this up, can you see how there's a hole in there? Now on this end it looks totally solid. It looks really similar to before. But when I come over here, you can see how there is a hole right in the middle. In fact, you can even see how the x-axis kind of goes in there. We could change this up even more, so check this out. Maybe I'll try to give you a clearer picture to see. What if I change this instead of 0.2x? What if I made this like 0.5 should work good? Okay, check that out. That's not going to be the greatest. Darn it. Let's see here. Let's do this. I'll change this up just so it's not confusing. So cosine of x, and check that out. It does kind of look like a yo-yo. So let's go cosine of x, and I'll go 0.5, but I'll go from, I don't know, how about 0.5 to 0.75 maybe? There we go. Okay, so notice how this is even more obvious, right? You can see the hole right smack in the middle. And we could extend this over to make it a little bit closer maybe. So let's just say 0.9. So we make the hole a bit smaller, but you can still see how it's got a hole right in the middle of it. Let me bring the rotation back. So here is, can you see my region right there? It's like grayish. And again, can you see how there is distance between the region itself and then the x-axis? Talking about this distance, there's distance right here. from on this thick red line, doesn't that represent the distance between the actual region that's being rotated and the x-axis? Okay, so this decision point that we're talking about here, where basically you're going to ask yourself the question, is my solid really solid? Is it genuinely a solid object, or is there a hole in the middle? Okay, so your answer to that question will determine how you do this. And let me talk about how you would think about this one. Let me go back to that rotated version. So here is the solid if you actually rotated it. Okay, so how we handle this, if I didn't have, how do I want to put this? If I just had cosine of x, kind of like we had before, wouldn't we say the volume is equal to pi times integral from a to b of r squared dx? It would be a solid shape. Now this one is not solid, and so we would not use this, at least in its current form. This would be if you truly have a solid. But if there is some kind of a hole in the middle, some kind of a gap or hole in the middle, what you're going to do is you are going to go with this, volume equals pi integral from a to b, and we're going to use big R squared minus little r squared dx, if we're using x's here. Now, why would we do this? It might be helpful for you to see this expanded out. Can't you do this with an integral? Can't you write it as volume equals pi times integral from a to b of big R squared dx minus pi from a to b, integral from a to b of little r squared dx? So check this out. Isn't this in the pink box, isn't this just the disk method? And then, isn't this thing in the blue box just another disk method? So the way that you find the volume of something like that has a hole in the middle is you find the volume as if the hole wasn't even there, and then you subtract the volume of the hole. And we're going to later on call this the washer method. And the reason why we call it the washer method is because these little representative geometric figures are no longer disks like what we saw with that previous graph. So there's a disk just like we had before with the x-axis or the axis of rotation going right through the middle. No longer will they look like this. There will be a hole in the middle.
They'll actually be CDs.
Say again?
They'll actually be CDs because of the hole in this.
What about the BCDs?
They'll be CDs.
They'll be CDs because there will literally be a hole in the middle. Absolutely right.
Nice.
Or you can think of this as like a washer that you would buy at Home Depot, right? The thing that goes on the bolt and the nut, right? That's literally what we're talking about is they're little washers. Okay, so the whole point of this is to help you visualize what we're doing. We haven't actually calculated anything yet. Are you okay with the visualizing part as far as what are we finding? What does it look like? Can I visualize this? Do I understand a little bit about why these formulas would apply? We doing okay with all that? Okay, great. So let's do some. So right here, yeah. If you want to, here, this is number 2, and if you want to see number 1, you need to watch the intro video. Number 2 is a nice one. Come on, there we go. So it says, region A is bounded by the x-axis and that graph. Find the volume of the solid formed by revolving region A about the x-axis. If you can just graph this yourself, that's great. Without a calculator, if you want to use a calculator to graph this, it's okay too. Just so you know, we'll never make the graphing of the region the thing that makes you fail or succeed on these. So usually supply a calculator or a graph. So one way or the other, get to where you need to be and see if you can visualize. Would this solid really be a solid, or would it have a hole in the middle? And once you've visualized that, see if you can kind of think, what would I do to get this thing set up and maybe finished.
Yes, sir.
So, Nick, let's talk about some strategies, and let's talk about how the numbers all work. And I usually make a note like this, that the axis of rotation is the x-axis. So, I don't know how you guys are visualizing this. If you wanted to, like if you're just thinking to yourself, man, I have a hard time seeing what this should look like, I would encourage you, I was just on GeoGebra, that was the thing I was just working on, and you can change the functions to just about whatever you want, within a reason, I suppose. So you could get onto GeoGebra and you could help yourself visualize what's going on until you can see it in your head. The question you've got to answer here is, will the solid that happens from this have a hole in the middle, or will it truly be a solid solid?
Solid.
Right? It's going to be totally solid, right? It's going to look sort of like a football kind of thing, or an egg, like a symmetrical egg, something like that. Okay, so once you've made that decision, once you've realized this will truly be a solid solid, what you've really decided is that you are going to be using the disk method, right? The disk method is volume equals pi times the integral from a to b of r squared. Sometimes I'll draw in a representative rectangle to help me visualize the little disk that's being created as the rotation happens, or maybe even a couple of them. So this is one thing I think was mentioned in the intro video, is that the representative element will always be perpendicular to the axis of rotation. Veterans, do you remember that? Representative rectangle or disk or whatever you want to call it will always be perpendicular to that axis. In this case, it's the x-axis. So what that does is that sets us up as far as our dx or our dy. How thick or how wide are those representative rectangles? They're dx wide, and so that means my little disks in there will have a height or a thickness of dx. So what that does is that sets me up to where I have to use x's on everything, right? That dx is what tells me what everything else has to be. So what did you guys put in there as your limits of integration? So here you go. Yeah, you can do negative root 2 to positive root 2. Then, what is the distance from the axis of rotation all the way out there to the outer edge of the region? Let's get to, you're going to be right, Sam, in the end, but check this out. This is going to be super important as you try to reason, especially with the washer method. Would you guys agree with me? Check this out. From red dot to red dot, isn't that literally, if we wanted to take it very literally, a y? Isn't that the definition of what y is? Measuring from the x-axis up or down a certain distance, right? But I know that I can't leave that with a y in there. So what is the thing, of course, Sam mentioned this earlier, what's the thing that y is equal to?
2 minus x squared.
2 minus x squared. So I'm going to replace that y with what is more appropriate, 2 minus x squared dx. Okay.
You do.
So guys, as far as how this can be assessed, there are lots of ways. One way would just be to say, set up a definite integral that is equivalent to the volume. And if that's the direction, then we did it, right? This is it. Of course, another way would be actually find the volume. And I must say that if it said these instructions, like it does say, find the volume, I would actually change my setup just a little bit. I would do this. You got it. I would go with this.
Good job.
So Santi saw this pretty quick, or maybe he already saw it. Why would I do this? Why on earth would I do this? One word answer.
Because it's an even function.
And therefore it has? Symmetry. That's right. It's an even function. It's got symmetry about the y-axis. So I can use that fact, cut my interval in half, and then double the result, right? That's what that 2 out front is. That's the doubling the result. This would make a lot of sense to do it this way, also because of the 0, right? That's going to make the back end FTC1, when you're actually plugging stuff in, a lot easier. Does this make sense? Okay. I don't think, just an FYI, I really don't think on a quiz or a test or the AP test that I would have you with these numbers, like I'm really speaking about the root 2 more than anything else. I don't think I'd have you evaluate this all the way through on a quiz or a test, simply because it would start to become more about the details of the arithmetic than it would be about what I'm actually trying to assess here. So please don't stress and ask, is this one going to be on the test? Because the root 2 really freaks me out. I mean, let's be honest. If I gave you enough time, it should be no problem at all, right? But I'm not going to give you gobs of time to sort through root 1/3 times root, or 1/5 times root 2 to the 5th, and all that sort of thing. Well, I almost do. I'm just kidding. Let's run through it real quick just to get kind of the nuts and bolts of it here. So if I actually found my antiderivative, I need to multiply this out. So this would be 4 minus 4x squared plus x to the 4th dx. Let's give you an example of how this could go and try to give you some practical advice on what you could do here. So it'd be volume equals 2 pi, and then your antiderivative would be 4x minus 4/3 x cubed plus 1/5 x to the 5th, evaluated from 0 to root 2. And I think you know where this is going. If this were a free response, wouldn't I just stop right here
100%.
and just say, well, this is, to the best of my knowledge, this is equivalent to the answer, and if you want to sort out what all those root 2's do, you can. And there would be some simplifying you could certainly do. I mean, root 2 cubed is really 2 root 2, so you'd get an 8 root 2 over 3. You could clean this up, and it would actually clean up pretty nicely. You're going to get something or other root 2 over 15, whatever. But as far as on a free response, you would be foolish to go past that step. And I'm just telling you right now, in a multiple choice, we're not going to do something with all these root 2's. Okay? Questions, concerns, visualization issues, what are we doing issues, why does it work issues, I don't know. Say again? Come on, you're not allowed to do that, Peyton. Like, make little comments under your breath, and when questions, say nothing. No. Wasn't saying anything. Okay, let's move on, and let's talk about the question of what if there was a hole
You just subtracted.
in the region. So let's see here. Let's
Give her a nice subtraction there.
get a subtraction in there. Yes. So we'll just do one of these, I think.
Subtraction doesn't exist.
Say again? Subtraction. Okay.
Let it.
So you,
All in your head.
I realize there's an intro video in here somewhere, and feel free to check that out. I'm getting a little bit ahead of myself because I'm not going to stop just because you haven't done the intro video yet.
Hey, you tell us.
The intro video does not tell me what to do.
You
I'll
are
just
not
keep-
bound.
We'll just keep going. Okay. So I want to do B with you. The intro video has A on it. And I think, so just as far as like thinking ahead, when we get to, that's not tomorrow, but Wednesday, we're going to talk about the thing that most of you mentioned. I mean, Meg, you were pretty vocal about this. Most of you have mentioned as a struggle, and that is, what if you rotate around something that's not the x-axis or not the y-axis, some other line, right? I think you mentioned that. So we're going to do that on Thursday of this week. There's some subtraction, and yeah, we'll talk about how all that works. But we'll do that on Thursday. We won't do that today. Okay, here we go.
Is this where the equal?
So here is a graph of my region. Actually, I'm going to change this just a little bit. Here is the graph of the region. So let's see here. You guys know these well enough to know which one is x squared, blue or red? Red is x squared. That's right. So these are actually inverse functions. So they should intersect where out there? 1, 1, right? And as well as at the origin, 0, 0, right? One of those lovely characteristics of inverse functions. Okay, so guys, we're doing B.
Does it matter which one I make the big R and which one I make the little r?
So let's talk about that. It very much matters. It very much does. Okay, and you'd see it pretty quickly if you mixed them around. Hey guys, let's finish well. Okay, so in B it says let's revolve this around the y-axis. So the other example we just did was revolving around the x-axis. This is revolving around the y-axis. So the details are going to be different. Oops, but the principles will... Why did that just totally disappear? Oh, lovely. Principles are the same. So here we go. Let's...
It was such a nice parabola too.
It was. I can usually make it come back, but...
Mr. Anderson,
Say again?
the washer method is like if you could put water in it, not necessarily.
Would it hold water? So the washer method, yeah, the question about the water would be, would it hold water or would water flow through it?
Yeah, I was just.
If the answer to either one of those questions is yes, then it's washers.
Okay, I was thinking.
And if you look at it and you're like, there's no way I could put water in or through that no matter how I rotated it, then it's discs.
Okay, I couldn't remember if it was just if there was a hole or if there's like a little bit.
Yeah, either one of those scenarios you're using discs.
Okay.
Okay, so revolving around the y-axis. So the principle I mentioned earlier was that the representative rectangle or the representative disk always has what relationship with your axis of rotation?
Perpendicular.
Perpendicular. Okay, so I am going to, the relationship between the representative rectangle and your axis of rotation, there will always be perpendicular. So I'm going to just sketch one in real quick. There is my representative rectangle. So that represents the part of the region that's getting rotated around. It would form, as we can probably see here now, this would form a washer, right? So you want to try to visualize this. And can you see how this orange space right in here, do you see how that orange space would also rotate as just space, forming a big gap right in the middle of this solid? So if you can visualize this and say, wow, is there a hole or kind of a big old concavity in there? Like Julia said, could you put water in this thing if you oriented it the right way? And if you could put water in it, you're going to be using washers. If water would just flow right on through it because there's a big old hole in the middle of it, you would use washers. If there is no way you could put water in this or through this, then you would use discs. Can you see how this would be like a really odd-shaped bowl? Okay. So because of that, we will be using the washer method. So I do have a way that I prescribe for the washer method, and it goes along with what I said earlier. It is so exasperating to me when I see this. I'm going to write this in red. I'm going to erase this. This is wrong. If I see, I hope you're paying 100% attention here, because if you're only paying 50%, you're going to get messed up. If I see washers and I just write this, I have a major issue. Okay? So here's, I don't know, if somebody told you, hey, just set it up like this, and then as long as you get the details right, you won't make any mistakes, would you do it that way? That's what I'm telling you. Just do it this way, and as long as you get the details right, you're good. So check this out. Once you identify it as washers, please just, for goodness sake, set up the washer method right away. So this would be pi times integral of big R squared minus little r squared. Please, just set it up like that. Don't try to do any details yet. Just set it up as big R squared. Notice I made my first parentheses big, and then my second parentheses are a little smaller, right? So big R squared minus little r squared. So the first thing I decide here is this going to be a dx thick representative element or a dy thick? And what do you all think? It's going to be dy, right? Because again, we're perpendicular to the axis of rotation, which happens to be the y-axis. So that'll be the first detail I fill in. It'll be dy. The next detail maybe could be the limits of integration, like where am I going to start accumulating these washers and where am I going to stop? So wouldn't the washers start down there and work their way up here to the very top? All these little representative rectangles? So at what y value would I start accumulating? Yeah, start at y equals 0. And where would I stop? At the intersection point, which happens to be y equals 1. It happens to be 1, 1. So we're going to integrate, or we're going to accumulate from y equals 0 to y equals 1. And the only thing remaining is handling kind of Jack's question earlier. Does it matter where the big R and the little r go? It definitely does. So let's see here. I'm going to say that, I'll use red here. Would you agree with me that from red dot to red dot, doesn't that distance right there, doesn't that represent the big radius?
Yes.
It's the big radius, right? It's from the axis of rotation out to the very outer edge of my solid. So, I'm not going to finish with this, so maybe don't write this in there. Quite literally, if I start on the y-axis and I measure out to the right somewhere, what am I talking about? I'm talking about an x distance, aren't I? So, literally, my x-coordinate, that would be that radius. The issue with this, of course, is that I've got a dy integral, and so I can't leave that x in there. I've got to convert this over to a y. Which equation is the red graph? Y equals x squared. So I want to take this y equals x squared and rewrite it with the x solved for. So this would be plus or minus root y equals x. It's not really going to matter because I'm about to square it, but do you think I should use the plus root y or the minus root y?
Plus.
Why?
Because of your bounds.
Yeah, first quadrant. We're bounded by the first quadrant. So over this positive. Yeah, exactly. Okay, so I will replace that x with what it should be, and that's root y. Okay? Now, the little radius, wouldn't that be from blue dot to blue dot? This distance right here? Well, how far is that?
X.
That's literally x, yep. But I can't leave it like that. Of course, now we're talking about the y equals root x. So how do I solve this? I'd square both sides. I could replace my x, which was well-meaning and correct, but not the right form, to replace it with y squared. Does this make sense? Okay, so then volume equals pi, integral from 0 to 1. Now it's really y minus y to the 4th dy. Volume equals pi. It would be 1/2 y squared minus 1/2 y to the 5th. Evaluated from 0 to 1. There we go. And of course, that 0 is going to just yield a 0. So if I actually evaluate this all the way through, it would be volume equals pi. It'd be 1/2 times 1 minus 1/5 times 1 minus 0. 1/2 minus 1/5, that would be 5/10 minus 2/10. So I'm getting y equals 3/10 pi. So that one wasn't too bad on the back end of actually evaluating it, namely because of the 0 and the 1. That helps, but we wouldn't always do it that. We wouldn't always take it that far. Okay, so how are we doing? Questions? Okay, so I think I put that in the wrong spot, didn't I? That should have been in B. Take all this. For anyone watching the video later, take all that and just drop it right there. There we go. Later on, you can just like draw the double arrow and say switcheroo. Okay. All right, so I wanted to stop at this point, I think, just to remind you that we've got our loop quiz, our one loop quiz of the semester, mañana. Wanted to talk a little bit about the loop quiz and what it is and all those things. If I remember correctly, this loop quiz covers up through chapter 5, which is, derivatives of transcendentals, integrals, but it doesn't cover It doesn't cover, like 8
We just did.
improper integrals. Yeah, it's called loop quiz because we loop back, right?
Top way wins, small lag, is that what it is?
You are correct in saying what you just said.
So it's not.
Correct. I didn't want to be like, well, you're not wrong, and have you try to figure out what that meant. What you just said is correct. So loop quiz is all multiple choice, completely objective. It is like timed, I guess would be the best way to put it. Like there's a very specific time, so it's not one of those ones like we had in the past where, hey, if you need a little bit of lunch to finish up, that's great. Like once you're done, you're done. The nice thing about that is if you get to the end and you had like 2 to do and there's only 5 seconds, can't you just go B, B, done? You can just guess, or CC or DD or whatever.
The last two V's that I just
I honestly have no idea what they are. Feel free to do if you want, but I honestly have no idea.
That's comforting.
Just everyone
It's
put
always
A
C,
on all.
never guess B, always guess C.
Well, then you would expect
For Anderson.
you would expect to get like about a 25%.
Wait, is it weighted?
That's what my student.
So let's talk about Sam's question. I don't know what you mean by weighted.
Or like,
Scaled, yeah. So the other thing about it is because this is for the first time this year, this is kind of like close to like AP stuff as far as like timing and expectations, and it's all objective and all that stuff. It is scaled. The scaling is not based on, oh my gosh, they did terrible, we better curve this. I refuse to do that because I feel really confident in what we're doing. If I'm measuring what you should know, then you should know it, right? But it is scaled simply because the AP test comes from this perspective. And I don't really buy this perspective as a regular classroom thing, but their perspective is make the test so hard that the very, very best of the best of the best, maybe on a perfect day, would get 100%. Maybe, right? It's like last year's AP test, there was like almost 500,000 of them or something like that for AB. And I don't know, there's like, 5 people worldwide that got 100. I mean, it's like the odds of someone actually getting 100.
6
That was
minutes.
I mean, it's like
Yeah, it's everyone on 6.
not only do you have to be really, really good at what you're doing, you have to have a great day.
Would they notify you if that happens?
They do.
They do?
They do tell you.
Oh.
They send you a little note that says, congratulations, you are 1 in 100,000 essentially. You got a perfect score. And they'll tell the school. And so nobody's ever done that at our school. No. I'm pretty sure that there have been some people that had to have come close. In April, he probably could just because he is like master test taker. He probably could. But we've had some people, like in the April stuff, we'll do like a final full AP test. It's worth 108. I've had people on that score like 103, 104 out of 108, which is just like super awesome, really impressive. I mean, that means they absolutely have it mastered. But even then, they're a human, so they didn't get it right. So that's why it's scaled, because in a mini way, it's kind of like that.
Is it that difficult?
No. So content-wise, it's a much smaller scope of content, and it's only multiple choice. It's not also free response. So don't look at this as like, this is just like the AP test. Like in a small snapshot, it's sort of like it.
Is there a calculator on a section of it? Is there,
If I remember correctly, it's no calculator, but I could be mixing that up because some of my loop quizzes do have like a part one or the other. So,
Okay.
yeah. Yes, ma'am.
The quest we just took, is there like corrections?
Are there corrections? No, not for requests.
Okay.
Yeah.
Can I get that back? I wasn't done.
Yep. Yeah, there's a couple of you that didn't get it back. So, alrighty, I think I'm good. Hope you guys have a great rest of your day. See you on Wednesday for your loop quiz.
for tomorrow, it's like, I need to study.